Hello, I want to talk a little bit about the project in this video. I know we haven't really spent much time giving real-time videos for the course this summer, so I want to be sure that I go over a few things. I thought it would be a little easier to do it via video than than through written instructions. So, as you know, we have 9 people in the class. Well, maybe you don't know. We have 9 people taking the class this summer, and I did a random division of that into 3 groups of 3. And I have identified 2 projects. So, if people like the projects that I've identified and am asking you to do, then basically you'll have 2 groups will be doing the same project, and then one group can do a different project. Actually, as far as I'm concerned, all 3 groups can do the same project. I just wanted to give you a couple of different options. So you are permitted to work in your group of 3, or you may work alone. So what you can't do, however, is you can't collaborate between groups. So if you wish to work in a group, you need to work in your assigned group, and you cannot share your work, and none of your work, not your data files, not your code, none of your work can be shared with any other group. And I checked that very carefully. I check that very carefully every semester, and I will say that I have given students zeros on projects before because groups turned in very similar, if not identical, parts of projects. It is not true that you will automatically generate certain kinds of graphs because these are open-ended problems, and so what you actually generate as an output depends on your original approach. So let's talk a little bit about what I want on the projects. You will need to incorporate a section that discusses background information. So you'll need to do some theoretical discussion. And as I go through each problem, I'll point out what that may be. These projects should almost certainly be done in MATLAB. I don't know of any other software that is widely utilized where I can actually grade your code that will be as straightforward as MATLAB will be for these projects because there are built-in tools. For example, the one we're going to talk about first, the wavelet analysis, there are several wavelet functions built into MATLAB. So let's talk about each individual project, and then once people let me know what you think you want to do, then I'll go in and I'll sort of re-gear and give you some more information specifically on the projects. But first I want to be sure that that there's a division and people want to do both projects. All right, so the first project, their first option is the use of wavelet analysis to identify time-localized phenomenon. Now, wavelet analyses are widely used in signal and image processing. They came around about 25 years ago. There was kind of a pivotal publication on different kinds of wavelets. And basically what they are is they're just little time-limited waveforms. And there are a set of lectures on wavelets in the section on transforms, as well as an extensive coverage of wavelets in the MATLAB tutorials. So if you go to MATLAB's tutorials, there's a lot of information there on the theory behind the use of a waveform. But basically what it's good for is it's good for dealing with situations where you might have a signal or an image or something that has a localized effect. So for example, if you're looking at brainwave patterns, the brainwave pattern is a stochastic signal, meaning it's statistically based, and it looks like, if you just look at it, it kind of looks like noise, kind of looks like bandwidth limited noise. When people have seizures, you will often see a short burst of very clean sinusoidal looking waveform, and it'll be, sometimes just for subseconds. You sometimes also will see spikes in the signal that are not characteristic of the signal overall. Now, that time-limited data is, if you're looking at it, if you as a human being are looking at it and you're looking at something like a time record, it's very clear to you when that happens. On the other hand, if you're doing something like a frequency-based analysis, then you can end up, if the time record is long enough, that localized effect basically gets lost in the transform and in the power spectrum. And so you don't even know it's there. You've just integrated over it when you've done the Fourier transform. So Fourier analysis and filtering are not necessarily the ways to either identify a local effect that you're looking for or get rid of a local effect that you don't want. So we're going to look at a project that sort of simulates an EEG, and you're going to create a simulated data set. So the first thing that you want to do is you just want to probably use a random number generation process, give it some limits, and MATLAB has one of these. And you want to set up an array of several thousand points where you just have this random stochastically generated signal. If you want an idea of how you should set up the array, it's reasonable to think about 5 to 10 seconds of data with a sampling rate of 1,000 samples per second or even higher. So if you did 5 seconds of data with 1,000 samples per second, that would be 5,000 points in your data array. Okay, then given that you know your sampling rate, and you can define that, it doesn't have to be 1,000, it could be higher. Given that you know your sampling rate, I now want you to filter the data using a bandpass filter or a low and high pass filter combination within MATLAB to simulate a signal that contains frequencies from 5 to 50 hertz. So you'll create this simulated data set, and then you'll filter the data to eliminate the higher frequency behavior. Now, once you've done that, I want you to add to the data set a spike. So we're trying to create a localized effect. And your spike should have an amplitude of about 5 times greater than the amplitude of your signal, and it should have a duration of about 10 milliseconds. And you can do this manually. You can go in at some point in your data set and just create a spiky kind of behavior. So you can just go in, literally, you can go into your matrix and change numbers where you're doing something like a triangular shaped spike. Or you can be fancy and you can define a function that will do the same thing. So I really do not care. The main thing is you just need to document very cleanly exactly how you did this. Now, what we're trying to do is we're trying to remove the spike. So we don't want the spike there. So the spike is there, it's superimposed in the signal. You want it to have a duration of at least 10 milliseconds, possibly longer. You probably want that. In fact, let me change that, because really, to really simulate this, you really want that to be about a tenth of a second. That would fall in the 10 hertz range, which would put you right in the middle of this bandwidth and give you a much better indication of what you're doing. Okay, so if you create that 100 millisecond spike and superimpose it on the signal, so you don't necessarily want to remove the random data points because you want the signal to be superimposed onto the spike. So if you created another array where you had zeros and then your spike and then zeros, and you add the two arrays together, you should get your original band limited noise signal along with your spike together. Now, the first thing that we want to do is we want to try to use frequency-based filtering to remove that spike. But you want to do that without impacting your 5 to 50 hertz signal. So you want to look at things like what happens if you use a very narrow band filter, and you can do this digitally, of course. What would happen? Can you successfully do that? Can you maybe use a high pass filter, or can you use a low pass filter? Is there some standard filtering method? So try different ones and look and see what happens. So how would you know how to look and see what happens? Well, you look at the signal before and after it's filtered, and maybe you look at the spectrum before and after it's filtered, and you try to ascertain, did you effectively remove that spike, which we're going to refer to as an artifact, or is it still there? So what you'll find is that it's very difficult to remove the spike using filtering techniques because the frequency, the fundamental frequency of that spike is about the same, kind of falls in the middle of your signal bandwidth. So if you do effectively remove the spike, you're probably also negatively impacting the signal. So once you've done that, what you want to look at is what advantages does the wavelet offer in order to remove that artifact. So you want to use a wavelet transform, and you want to decompose the signal into different levels. And after you read some of the lecture notes and watch the videos on wavelets, that terminology will make sense to you. Once you decompose the signal into different levels, you can employ a wavelet filtering technique where you essentially zero out the level that contains the spike and then reassemble the signal. Now you can do all of this within a wavelet toolbox in MATLAB using the toolbox only. However, the toolbox is a little bit like a black box. So you need to be very sure, because I will ask you on this, you need to be very sure that you understand what the toolbox is actually doing when it does the wavelet filtering, because the toolbox gets into some different types. They have wavelet trees, they have much more complex. We just want to do a simple wavelet transform, continuous wavelet transform, by the way, in order to try and identify and possibly remove the spike. All right, so that's one project. So if you're interested in wavelets, as I said, they've been used in signal processing, they've been used in image processing, they've been used in generating features and pattern recognition problems, and so on. The other option is using something called principal component analysis. This is another project where you will generate a set of data. So what you want to do is you want to use principal component analysis to separate out mixed signals. That's what it's good at in some cases. So we want to look in this case. So you're going to create a set of signals. So you're going to choose 3 sinusoidal signals that have different non-harmonic frequencies. So you don't want 5 hertz, 10 hertz, and 20 hertz. You'd want 5, 13, and 21 so that you're not harmonic. And you can call those signals A, B, and C. And then you want to have another signal that's a single pulse, or maybe a series of 2 or 3 pulses, randomly spaced. You want to call that signal D, and then you want a random noise signal, and we'll call that signal E. And now what you're going to do is, using these 5 basic signals, and by the way, the time length should be the same on all of these, the number of points in the array, and the amplitudes should be similar. So you don't want one to be an order of magnitude off from another. Now what you want to do is you want to create 5 signals by mixing these signals. So I take the signal A and I multiply it by some constant, and I add it to signal B multiplied by another constant, and I add that to signal C multiplied by a third constant, and so on. And I want to do that 5 times where I generate 5 signals. And the C's need to be different, and they should be between 0 and 1, and they should not be more than, say, an order of magnitude apart. So you don't want like a C of 0.001. You might want to use 0.1 as your sort of your lowest value. And you don't really want to be much more than 1. So we're trying to keep everything kind of the same order of magnitude here so that you can see the mixing and the unmixing. And then you're going to use principal component analysis, which is a toolbox within MATLAB. You're going to use principal component analysis to unmix the signals. So as there will be, additional information provided on principal component analysis and what that is. This is used for things like blind source separation. So if you have, for example, an antenna array and multiple signal sources, and so your antenna array is actually picking up a mixture of multiple signals, then this is used to try and separate out what are the original signals, because oftentimes we don't know the location or the magnitude of the original signals that got mixed. So this has to be done in other ways, and principal component analysis is one way. You will find that it has some weaknesses, particularly in this kind of problem where we have sinusoidal waves, which are highly deterministic. You'll find that PCA struggles to separate out sinusoidal waves of different non-harmonic frequencies. So I'll just give you a heads up that this may or may not work well. Mixing the pulse in there brings in some interesting things as well. So like the previous project, I anticipate that you will have a section where you go over the theory of principal component analysis in the introductory part of your project. You'll have some code where you generate your sample data set, and then you will have some results, and you should submit also an M file that contains all of your code on both of these projects. You should submit your results, and then you should have some discussion of your results. So there's no reason you can't get started on these right away. I will provide you with additional information and point you to the appropriate lectures to watch in order for you to get started on this. Particularly, you can get started creating your random data sets. So if you guys will let me hear from you regarding are you going to work in your group or do you prefer to work alone? And then if you will let me hear from you on what project you would like to choose, then I can point you to some more resources and get you some more information.